Hi everyone. In this tutorial, we'll be discussing a kind of introduction to Hugging Face library. So Hugging Face is a very useful library when we work with basically the transformers based model, mostly the transformers based model. All these models, open source models, data sets are available on something called Hugging Face Hub. So we will see how we can use this Hugging Face library to load the models, to fine-tune them using some toy examples, how to load the data sets, and how to use it for inference. So let's start. So here, that package in Hugging Face which deals with transformers-based models is called transformers, and there's a package called datasets which deals with all the open source datasets. So we need to first install them. Let's first look at the whole pipeline, whole flow of how we process input. So first we have this raw text, so this course is amazing. And then we have a tokenization algorithm which breaks the text into some tokens and map it to some numbers, right? So these numbers represent a token, right? So this course is amazing. Suppose we apply some tokenization algorithm, say like byte pen encoding or something, or a sentence-based tokenization, something like that, and it maps it to a sequence of tokens, and tokens are represented as numbers, right? So these numbers are basically kind of a dictionary mapping only, right? Nothing else. So 101, say this tells this is a token and its number is 101, something like that. So we have then a list of input IDs, and then these are passed on to the model. So when the model gets the input IDs, which is a list of token numbers, what it does, it goes to its embedding matrix, does a lookup. So the embedding dimension of the token is already stored in the embedding matrix of the pre-trained model, right? If it is not pre-trained, if we are looking to train it from scratch, then the initialization is some random initialization or some informed initialization like Xavier initialization or something like that. And then when you train the model, these embeddings are also updated. Embeddings of the token are also updated. So for now, let us assume that the model is pre-trained. So once we pass the input IDs, the model maps the token IDs to token embeddings. And then the token embeddings are passed on to the model. Position encoding is added in case of transformers, and whatever the model architecture is there, whether it's an encoder-decoder model, whether it's a decoder-only model, whether it's an encoder-only model, it is processed accordingly. We have already seen in a lecture in, I guess, 1 or 2 weeks ago, that how do you implement transformers from scratch using PyTorch, right? There we saw how within the model, how a transformer layer is implemented, right? We saw every component of it: multi-rate addition, positional encoding, layer normalization, encoder block, decoder block. We saw all that. So now we are putting all this together into a single model, right? And there are simple variations within the model, like say GPT-2 doesn't use rotary positional encoding or rope, whereas Llama uses rope. Mistral uses sliding window attention. So there are all these slight variations in the architecture, in the kind of attention they use. Like Llama uses group query attention. So all these variations are there. But let us assume that within the model, we have a kind of a function, a module, which takes the input IDs, maps it to the embedding, add the whatever position and encoding is defined for that model, processes it, and the final output is a logits over the vocabulary token. So suppose there are 32,000 tokens in the vocabulary of a model, right? So then the output will be a series of logits over these 32,000 tokens, and then it is passed on the softmax. The softmax maps these 32,000 logits into a probability distribution over the 32,000 tokens, right? So it will say, okay, so token I has probability 0.3. Token this has probability 0.2, and just like that there is a probability distribution over the whole vocabulary set. And then you can do some post processing. So if you are so to start with, we will take the example of the sentiment classification task. and try to do sentiment classification using an encoder-only model like BERT, right? We'll use Robota here. So Robota, just think of it as a variation of BERT, right? The architecture is same as BERT, right? So we have already discussed that BERT is trained using masked language modeling. And so what BERT does is it gives you a representation of an input sentence, right? And then you can train some linear layers on top of the BERT to do any classification task or anything you want to do with the sentence representation, right? So this is the flow. So once you have the a sentence representation, you can use it to make some predictions or stuff like that, right? So let us now load the model and the tokenizer, right? So there is something in transformer library called auto tokenizer. So what auto tokenizer does is when you give the model path, right, we'll see where does the model path comes from. When you give the model path, it automatically it has some kind of dictionary defined, so it automatically looks into what tokenizer is trained for that model, right? So during pre-training there is a particular tokenization algorithm used. So when you're doing inference, you need to use the same tokenization algorithm. So tokenizer, auto tokenizer handles this. You can also explicitly say, like for here using say Robota, so you can explicitly define what tokenizer you need to use, but auto tokenizer makes our job easy. And we have auto model, which again takes in the path and loads the corresponding model in that path. So auto model again does our job a little easier. You could have explicitly defined it, and here you write what is the task. So the form is that you write auto model and then you write for and the task you are trying to do. It can be sequence classification, it can be masked language modeling, it can be causal language modeling. So it can be auto model for causal LM, it can be auto model for mask LM, it can be auto model for sequence classification. So it's auto model for the task you have, right? And you initialize the tokenizer as tokenizer is the auto tokenizer dot from pretrained. So from pretrained is a method defined in the auto tokenizer class. So dot from pretrained, and then you pass the path to the model. So the question is, where do you get the path to this model from, right? So normally in the web, if you search Hugging Face hubs, right, you will have this Hugging Face hub. So there you can get list of all models, right? So if you go to models, so you can see the tasks, you can filter by task, you can see the data sets, you can see the models and all things like that. Suppose you want to do natural language processing task of text classification, then if you go to models, you have all these models, right? And we will be using one model which is trained on Robota. So you can search here, right? You can search Robota sentiment Robota large English, right? So we will be using this model. So this model has been trained on sentiment analysis task. Robota is basically architecture is same as BERT, and it's trained on English. So how can you use this model? Just go to this use this model feature in transformer libraries, and there you can see that, okay, so this is what you need to do. You need to tokenizer, so this is what you need to do. It says Hugging Face. So just copy that, you just paste that, and this is what we have done here, right? So that's how you can search a model from hub and use it in your code, right? So running it will just load some binary files corresponding to the model. So it takes some time, so let it load all the files and let us proceed, right? So how does it as I said, what are the steps? Let us think step by step now, right? So the first thing is you tokenize. So suppose you have an input sentence, I am excited to learn about transformers. So what you does is you pass the input to the tokenizer, right? And this return tensors is equal to pt. What it does, it says that, okay, return the output in the form of PyTorch tensors. If you don't write it, it doesn't return as tensors, it returns as normal list. And then outputs, to get the outputs, you pass the model the unpacked list of tokenized input. We'll see this in more detail. And then the prediction is basically whatever logits you have, you take the max of that and map it to the label negative or positive, right? So this is what, okay, what is saying that no torch is not defined. Maybe I'm not run this. Okay, now it should be fine. Right. So torch was not imported, so now it should be fine. So now if we do torch or sort max on the outputs, so you get this logic. So it says, okay, I'm excited to learn about transformers. If you look at the sentiment of it, there's a 0.0012% probability that is negative and a 0.9988% probability that's a positive, right? So that's what is done. So let us look at step by step now. So this is the input. The input was, I am excited to learn about transformers. So when I pass it on to tokenizer, right, the tokenized output is like that: 0, 100, 437. So these are the list of token numbers, as I said. And the attention mask, if you remember, we discussed in our transformers from scratch tutorial that the attention mask, there are two kinds of things it handles. So when it's in the encoder side, it handles whether you have a padding token or not. If you have a padding token, the attention mask will be 0 there. If you have a future, like for causal language modeling, when you are doing decoder in the decoder side, there the attention mask will tell you whether to mask the future tokens or not, right? So for the future tokens, for a current token, all the future tokens will be zeroed out. So when you give sort max, it gets minus. It first, within the implementation, we make 0 to minus infinity in the attention scores, and then applying sort max makes it 0 attention in the attention matrix, basically, right? So this is the tokenized outputs. And then when a model outputs are when you pass on to the model. So what is the output? The logit over the whatever distribution you have. So this is a model for sequence classification. So we already have a two-dimensional output linear layer. So it outputs a two-dimensional vector, two-dimensional logit, right? So it outputs a tensor which is two-dimensional because it's a sentiment row data, right? And then the prediction is the arg max of that, the logits, right? So now we will basically divide this lecture or tutorial into 2-3 parts. The first part we will look at tokenizers, right? So tokenizer, like as I said, you can either just import auto tokenizer and play with it, or you can explicitly say, okay, this model I know uses distill BERT tokenizer. So here we are using the distill BERT model. So distill BERT is basically the architecture is the same as BERT. It's trained with knowledge distillation from a larger BERT model, right? So think of it as simple BERT. So BERT BERT. So it's an encoder-only model, right? Mask language modeling pre-training objective. Yeah. So connect with whatever you already learned in the previous weeks. So this BERT is an encoder-only model. So you can either use the distill BERT tokenizer, or you can just tell the auto tokenizer and just pass it, right? So you can see that, okay, there are some tokens, they are special tokens like pad token, unc token. Unc handles unknown words in the vocabulary. So if there is some token which is unknown, then that's how it's handled. There is a, we'll see the classifier. You probably during the BERT lecture you saw that what is the classification token do. The classification token is a token added in front of the input sentence. So it captures the representation of the whole sentence. So we can use the representation of this classification token only to classify the sentence or do any kind of classification task on the sentence, right? Separator token separates into sentences, so it's generally at towards the end of the sentence. And mask is basically masking the forward tokens if you do some generation task, things like that, right? So now suppose we have the input string NPTL is great, right? So I pass the input token, input sentence, the raw input sentence to tokenizer. So during tokenization, if we say return tensor is equal to PT, what it does is, look, now it makes, so if we remove it, right? If we remove this, it was just list. And if we add return tensors, what it does is it just converts it into PyTorch tensors, right? So that's the difference. So the attention mask tells you, okay, you need to attend to all tokens. There is no special token. So whether you do tokenized inputs dot input IDs or so this tokenized inputs is basically a dictionary, right? So tokenization, when you pass on to the input string onto the tokenizer, it runs a dictionary. One key of the dictionary is input IDs and another key is attention mask. So you can access the input IDs just to like access any value in the dictionary. And then you can define, okay, what is the classification token ID? The classification token ID is used to, the classification token, as I said, is used to do any kind of classification task. So classification token contains this whole sentence representation, and separated token separates two sentences, right? So first, the tokenizer, what it does is tokenizes into a list of numbers, token numbers. And then we have the input IDs, right? So we are seeing what is the step. And then what the tokenizer does is, so you have NPTEL is great. It first tokenizes it into N, P, TL, is great, that kind of tokenization breaking. Then what it does is, it adds a, in case of BERT tokenizer over here, what it does is it adds a CLS token at the front and a separated token at the end, right? So we can see this. So this is the steps. So the first, this is a start sentence, NPTEL is great. When you tokenize it, it tokenizes into N, PT, EL, is great, right? So these are some special tokens which handle. And then it is converted to, these tokens are converted to IDs. So N is 487. So you can easily check, right? You can easily check that tokenizer dot decode, and you can pass on the input IDs, right? You can pass on the input IDs, say 487, right? This is a 487, so it should give N, right? 487 is corresponding to N. Similarly, if you pass on, say 328, right? So what should 328 give? It is the exclamation mark. So you can just see it. Look, it's the exclamation mark. So just like that. And in fact, you can check what is the size of the vocabulary of a tokenizer, right? So you can just do get vocab and just make take the length of get vocab. Then you can see, okay, so there are 50,265 tokens in the DistilBERT tokenizer, right? So DistilBERT tokenizer can handle 50,265 tokens. So that's how you can see what are the number of tokens in a particular tokenizer, how much known tokens are there, right? So these are steps of the tokenizer. So once you have the converted the tokens to IDs, what the BERT tokenizer does is adds a 0. This 0 corresponds to, again, you can see that over here, as I said, tokenizer dot decode. What is a 0? 0 is basically our classification token. So classification token or the start of sentence, you can also see it as start of sentence. This acts as our classification token. And this 2 is our separated token. So there's a kind of end of the sentence kind of a thing. So that these two are added to the start, there is a classification token, towards the end that is the separated token, and that is the final tokenized sentence, right? So if we already discussed that if you do return tensors, you'll do PT, the input IDs and the attention mask instead of a list are returned as a torch tensor, right? In fact, you can pass a batch of inputs to the tokenizer. So instead of passing a single sentence, you can pass 3 sentences. So that's how training works. Like, right, there is a batches of sentences passed together. So that is how we exploit the parallel processing power of GPUs. Right, we pass inputs as batches. So you can pass 3 sentences, say. NPTEL is great. Learning transformers is fun. We will learn about RLHF next week. So there are 3 sentences. And we do padding equal to true. But what padding equal to true does is, we already discussed in the transformers tutorial on implementing using PyTorch. So padding, what it does is, if the number, if the 3 sentences, suppose in this case there are 3 sentences. So one sentence is smaller than the other. So the smaller sentence will be padded with pad token IDs, which we will set here 0. So the pad token IDs is 0, say. So then it will be padded with zeros at the end to ensure that all sentences in the batch have the same length. And what truncation do is we define a max length. If any sentence after tokenization is greater than the max length, right? Number of tokens is greater than the max length, it truncates to the max length. So that's what padding and tokenization do. So just see here that pad token ID is set to 0 over here, and if we run this, see the pad token is pad and it is pad token ID is set to 1 over here. Okay, so here the pad token ID is set to 1. It's not 0, it's 1. That's so fine. It can be anything. It can be 0, it can be 1. It can be 2, it can be 3000, anything, but it is tokenizer dependent kind of a thing, right? So after padding, what happens is you see, so this was our sentence, NPTEL is great, right? There is this initial CLS and there is this 2 separator and this 1 are padded. So the largest sentence is the last sentence. We learn about RLHF next week. So there is no padding over here. There is no 1 ID token, right? And just look at the attention mask now. So in the first sentence, there are 3 ones, right, towards the end, right? And what attention mask does is it places 0 in place of the pad tokens. So it tells the model, okay, these are the special tokens, unnecessary. You don't need to pay attention to this while processing, right? So this reduces the noise during training and also the unnecessary computations for using these tokens, right? This is so okay, these are after tokenization. This is tokenization of batch, and you can batch decode. So you can just pass on whatever output the tokenizer gives as a part as a matrix, whether the rows are corresponding to each input examples. And when you batch decode, this is what you get. So CLS. So if you batch decode, okay, so this is what you get. This is the start of the sentence. Okay, this is basically CLS. NPTEL is great. End of the sentence is basically a separator, and then 3 pads, 3 pad tokens, right? Similarly, landing transform is fun. Is there a CLS? There is a separator. There are 4 pad tokens. And similarly, there is no padding in the last sentence because it's the maximum sentence length. So when you do simple batch decoding, you have all these special tokens shown in your output. But if you just pass on an argument, skip special tokens equal to true during the decoding, then during output it skips those all pad tokens, CLS tokens separate, it skips and this just gives the raw text, right? So this is tokenization. So this is the first part, right? So if we go back to our image, we have already dealt now that how do you tokenize the raw text into input ID. The second part is passing it to the model. Now we'll tackle models. So as I said that it's generally auto. What is the name of the module which handles that? It is auto model. What is the name of the class? You can say auto model for task name. So auto model for sequence classification, auto model for causal LM, like that. Or you can explicitly say instead of auto model, key we are using distil BERT here. So you are saying, okay, it is distil BERT for sequence classification. It is a distil BERT for masked LM. We can say like that. So this diagram kind of illustrates how does a model architecture look like. You have a model input, you have the embedding layer over here, and then you have all these layers. So in case of encoder-only model, there are n stacked encoder layers, right? And then you have the hidden states, which comes up to the layer, and there is a head. So head is basically a kind of feed-forward layer or some linear layer, feed-forward network, MLP, or a single linear layer, which just maps from the output vocabulary dimension to the, say you are doing classification on 2 classes. So it maps from say 1024 to 2, output dimension to number of classes for classification, and then there's the final model output. So that's how this whole model architecture looks like. And as I said, it is generally star can be auto model. So star for the task name, star for masked LM, star for sequence classification. In place of star, you can just keep auto model or you can keep the explicit name of the model like DistilBot, like GPT-2, right? Like T5 and things like that. So yeah. So how do you load the model? I already said you just need to define that class, right? You will do make an instance of this class like auto model for sequence classification, and then there is a method dot from pretrained, and you pass on the path. How do you get the path? If you have stored it in your local some checkpoint, you already stored your local environment, you just give the local path. If you don't have it stored, you get it from Hugging Face Hub, right? And when you are doing sequence classification for these models, you also need to tell what is the dimension of the head, how many labels are you expecting as the output, right? So this is how you load the model. And then what are the inputs to the model? The input is after tokenization, that is the input. What is the output of the model? You just pass on. So what should you pass to the model? You should pass to the model the input IDs which are achieved after tokenization, and the attention mask to tell which tokens to ignore during attention computation. You can either tell it explicitly, input ID is equal to model inputs or input ID, attention mask of this, or you can just do a simple star model inputs. So what star model inputs does is model inputs a dictionary. So star basically unpacks the dictionary, and the corresponding arguments are passed on, are mapped on accordingly, right? So you can just print the model inputs and the model outputs, and just to check, this is the distribution over the labels. Okay. So this Hugging Face transformer models works this is basically in the backend. This is a PyTorch, right? This is everything is written in the PyTorch. So this works very well with PyTorch modules. Okay, these are basically just PyTorch modules renamed in some classes, right? So they have inherited the NN.module class and written their own classes, just like we did for transformers when we implemented transformers from scratch in a previous tutorial. So Hugging Face has also done that. So this works very easily with PyTorch training loops. So we already know how do you train a model using PyTorch, right? So you have a actual target label defined, you have a loss defined, right? So here, suppose we use the cross entropy loss. So cross entropy loss between the model output logits and the label, right? And then you get the loss, you do backward pass. So what does it do? So how do you train a model? So you have a model defined, right? In PyTorch, what do? You train a model defined. You define a loss function. Okay, I want to do cross entropy loss between the model outputs and logits. You define optimizer, right? Optimizer, say Adam, and you pass on. You specify the parameters. What is the learning rate of the optimizer? Steps. What is, if you want to have any weight decay or not, and you pass on the model parameters to the optimizer. Then what does the training loop do? You first initiate the model, right? You take an input batch, you pass the input batch to the model gives some output, right? You calculate the loss between the model output and the gold outputs, which you already have as labels, right? Then you do optimizer.zeroGrad, so it ensures that the gradient in all tensors is set to 0, right? Then you do optimizer.step. So what does optimizer step do? It does a single step of updation, right? So before optimizer step, you need to calculate the gradient. So for that, you do loss.backward. So first you have optimizer.zeroGrad, then we do loss.backward, right? So optimizer.zeroGrad sets the gradient of each tensor to 0. Then when you do loss.backward, what it does is takes the loss and do a single back propagation. So the back propagation now populates the gradient field, right? So every tensor has this gradient field, right? Is defined a gradient function, and there is a gradient is stored within each tensor. The tensor is basically an object. So this gradient for each tensor after doing back propagation is stored, and then when you do optimizer.step, it updates the trainable weights as whatever the equation of the optimizer is. It can be simple gradient descent, stochastic gradient descent. So it can be simply the parameter minus eta. Eta is the learning rate. into gradient of that parameter. It can be simple like that, or it can be more complicated in terms of momentum and wet decay and things like that. So this is how it works. So you can just do loss.backward to see to do a single step of backprop, and you can also print the loss using this cross entropy. In fact, when you do model a single forward pass to the model, Hugging Face automatically computes the loss. So if you pass this model inputs to the model outputs, if you see, is already have this loss computed, you can see, right? So it makes our job Hugging Face makes our job a little easier by implementing a class on this PyTorch modules, and which gives the loss already as a part of the model output object, right? Now, one thing which is very good with this transformer module of Hugging Face is that you can access like every inner component of the model. So you have this model. So setting this model.eval sets it into a non-training mode. So it sets the request grad equal to false, right? So now there is no gradient computation. So that's what torch.nograd also does. So when you pass the model inputs to the model, you can access the hidden state. So if you print the model output, right, this is the model output. If you print it, right, what you see is, I can maybe show you a little bit. So it's a big model output, and if I go on top of it, right, look at this. The hidden state per layer is 1,8,768. Attention head size is this, right? And just look at here. So the base model output, what do you have? You have all the hidden states which are computed for each layer, after each layer, and also we have the attentions computed for each head, right? So you already have that in the model output, right? So this is the tokens you already said, yes. So in fact, you can just see the number of layers and the number of heads in the model. So a easier way to do that can be just go to model.config and just you can say n layers. So Distilbert model has 6 layers, so 6 encoder blocks, right? And if you do n heads, it says 12. So each layer has 12 attention heads. And in fact, you can access these heads of each layer and print the attention matrix which is computed by each head when you do a forward pass. So maybe you can look at the code. It's very simple. We just take the attention matrix which is computed by each head and just plot it using a heat map in PyPlot, right? The number of, this will give you the number of layers in the x and the number of heads at number of layers in the y-axis and number of heads in the x-axis. That's fine. So now we will just look at a simple task of fine-tuning. Till now we saw how do you load a model, how do you use tokenizers, and how do models process the inputs, and how can you access the internals like the attentions and hidden states in a model. Now we'll see how can you fine-tune a model on some particular dataset. For this purpose, we are using a dataset called financial phrase bank, right? So you can also find this dataset on Hugging Face Hub, right? If you go to Hugging Face Hub, if you go to datasets and just search by financial phrase bank, right? Financial phrase bank. So there, this dataset we are using, right? So we are using this dataset. So the way to load dataset is just to use the load dataset function. After loading, if we print what a dataset is, so dataset is basically an instance of the class dataset dict, and it says that it is a trend split which we are using. Each example within the data set has two features, a sentence and a label, and there are 2 to 6 4 examples basically within a data set. We define a truncate function which basically restricts the size of each sentence to maximum 50 tokens. We take 128 random examples from 2 to 6 4 and use it as a trend set, and some 32 examples we use for validation split. So we split that data set into two parts, training and validation. So this is a very standard practice in ML, right? And like this we can see that what the first say 10 sentences look like. So if we run the whole of this and then run this, okay, so this is the first 10 sentences. So an example sentence is, suppose the combined capital of these funds is expected to be 100 million to 150 million euros. So this is a kind of financial stress sentence, and this one label indicates that it's a neutral, 2 indicates is positive, and 0 indicates is negative, right? So this is how the data set now looks like: sentences followed by their labels, right? Then what do you do for each example in the data set? We need to tokenize it, right? So we define, so there is something called map. So inside the map you can define a lambda function. You must be aware of lambda functions in Python, and what the lambda function does is, so the argument to the lambda function is each example, right? So we pass through the tokenizer the sentence component of each example with padding and truncation, and we use a batch size of 16. So when we map the data set through this defined lambda function, it is first tokenized and then it is batched. That is 16 sentences or 16 tokenized sentences are put in each batch, right? Then we remove some columns and just format the data set, so that now the data set, after removing the so what do? We remove the sentence column because we don't need the raw sentence now because we already have the tokenized input IDs, right? And we rename some columns, and the format is set to torch, so all are like now PyTorch tensors, right? So now how does the data set look like? So now the data set looks like we have the labels in the form of PyTorch tensors. We have the input IDs, so there are the 16 input IDs in each batch, in the 16 list of input IDs in batch. So if we see the first two examples, this is one sentence, the input ID zeros are the padded tokens, and another, and this attention marks tells you. So this is how we have the data set now. And there is something called data loader in Torch, which you already know, which basically passes this batches of data, feed these batches of data into the model while training, right? Now how do you train it? We already discussed in the PyTorch tutorial, and also in this tutorial I was telling you that what you do, you define optimizer, you define a learning list scheduler, and for each epoch what you do, you do the model.train, that is now you set the request grad equal to true for all parameters. And for the batches, you first pass the batch to the model, initialize the gradient of the tensors to be 0, and then do a backprof, right? And optimizer step updates the weights using the gradient computed by the backprof, and then learning a scheduler if there is a word decay or stuff like that, and then you can evaluate. So this is a standard PyTorch training loop, right? You can pause and maybe see this code again, but this is a standard PyTorch training loop which you must be very familiar with by now, right? Okay, so that's how you train the model using PyTorch. But then HuggingFace provides something more powerful. It's provides something called a trainer class, right? So the trainer class will be enough to handle most of these fine-tuning and training works, right? So for trainer class, what do you need? So you again load the data set, and this small data set, you just have that train test split, and similarly we define this lambda function where this tokenized, right? So after tokenization, you need to specify your training arguments, right? So for using the trainer class of HuggingFace, so what do you need to specify for training arguments? You need to specify the batch size. So per device we are using 1 GPU here. There can be 8 GPUs, right, running in parallel. So that's what this per device thing does. And then you don't need to specify the number of training epochs. The evaluation strategy basically calculates the validation score for each epoch, right? And then how do you save, what is the learning rate, and things like that. So in the trainer class, you pass the model and all these training arguments you have defined, right? And then you basically pass the tokenizer and what is the compute metrics you want to do. So I won't run this because it takes a little bit of time for that, right? So I won't run this here. You can just pause the code, pause the video, type the code, and then run it yourself, right? So this is what the trainer module does, right? Now you can also specify some callbacks, like some checks on the validation accuracy, and maybe early stop your training or things like that. You can add that using trainer.add callback, right? Like early stopping callback. Patience equal to 1, because you can wait for one epoch maybe to see if validation accuracy is decreasing or not, and if it's continuously decreasing for 2 epochs, you can stop. And there is some threshold you can, so you can maybe read the add callback documentation a little bit if you want to use this early stopping functionalities. And then if you call trainer.train, so I have already run that. In this way, you are told the validation loss and the accuracy corresponding to it. And the evaluation is also pretty simple. You just do trainer.evaluate, and it will automatically evaluate on the validation data. If you want to predict on some data, you just do trainer.predict and pass the test set, right? So in the evaluation metric over here in the trainer function, if you remember, over in the trainer argument, in the evaluation strategy, you already specified epoch, and over here compute metrics, you already specify the metric on which you need to you want to evaluate on, right? So the evaluation and the prediction is also made pretty simple using the trainer module. I strongly suggest that you go to the documentation, Hugging Face documentation of Hugging Face trainer. It's very simple. You just search Hugging Face trainer, right? And you will be directed to this trainer module. So you go through this documentation once to make yourself familiar with all the parameters it takes in and how do you use that, right? It will be really helpful. You can pause the video and run this yourself on your Colab notebook, right? So after prediction, you get the results and stuff, right? Now before ending, so all these things we did till now, right? So like this, you can have a test example. You can just load the fine-tuned model which you have saved during training. So the checkpointing is the stuff. So here if you see again, we wrote that load based model at end is equal to true and saved strategy equal to epoch. So we are saving this. The checkpoints were being saved. So after 8 epoch we saved a checkpoint. So you can load that in this way, that from pretrained you then specify the local path. As I said, if you have a local path, you can specify that, and then pass the input string to the tokenizer, and you can predict and see. So these are all using the encoder-only model. Now, how do you use a decoder-only model? Say you are only you want to just generate stuff, right? Generate text. So there also it's pretty much the same. There also you need to specify auto model for, but now the task is just causal LM, right? So causal LM is basically the task of next token prediction. So you just load the auto model for causal LM class, and there from pretrained you can specify any decoder only model. Suppose we use GPT-2 over here, or say distill GPT-2, right? And then how do you basically pass on the generate? So there is some function called Model.generate. So within the Model.generate, what do you pass? You pass the tokenized prompt, unpacked tokenized prompt. So first you suppose once upon a time is your prompt. So you tokenize the once upon a prompt thing. So this GPT-2 tokenizer is basically auto tokenizer from pretrained GPT-2, like similar, very similar to what we did for decoder only model. Only difference is the model loading, during model loading you have to specify auto model for causal LM, right? So you just do Model.generate, pass on to the tokenized input IDs, what maximum length, how many maximum tokens you want to generate. So I just restricted to 50, and this do sample equal to true basically does sampling. So it doesn't do, if you do sample equal to false, it does greedy decoding. So we have already discussed greedy decoding, right? So here I do sample equal to true and top p is equal to 0.9. So we have already discussed nucleus sampling or top p sampling, right? So there is specified. You can also specify the temperature parameter instead of top p. You can specify temperature equal to 0.3. You can specify instead of top p, you can also use top k sampling, like top k is equal to something according to what you want it to be. So here I do nucleus sampling, and there I basically generate 10 possible completions of once upon a time, right? So if I like once upon a time, if you of such great uncertainty, for that reason the truth of this matter or something, the GPT-2 is generating. So this is basically a sentence completion task where you give a prompt and you expect the model to complete the prompt or generate something based on the prompt, right? Now there is something called pipeline in HuggingFace. So the pipeline function or the pipeline class basically automates your whole pipeline for a particular task, for some popular task. Like suppose we are dealing with the task of sentiment analysis. So HuggingFace has already a full pipeline written for sentiment analysis. So you just take the pipeline class, you call the pipeline class, you pass the argument, the task name and the model, right? So suppose the task name here is sentiment analysis and the model is say sentiment robota, right? So you pass that into the pipeline, and then you can simply to this object sentiment analysis, which is an instance of the class pipeline defined using the class name and the model, you can simply pass the sentence and get its predicted output, right? So there are many pipelines defined for many popular tasks, but generally since when we do research we define our own tasks and things like that, these are not always useful. But when you are doing some fast coding, want to get your things up, there is some already very well defined task you want to test upon, you want to be really fast, then this pipeline function becomes really handy, right? And to end with, I will also show you the masked language modeling. So for causal language modeling task, we were loading auto model for causal LM. For masked language modeling, what will be it? It's very simple, very trivial. Auto model for masked LM, right? So there also the tokenizer you call, suppose you are using BERT, suppose. So you call the BERT tokenizer and the auto model for masked LM from pretend you just give the BERT base case, whatever path you have. And what is the masked language modeling objective? The masked language modeling objective is within your input sentence or prompt, whatever you call it, there is a mask token, right? Now the task of masked language modeling is to predict possible tokens in place of the mask token, right? So basically where there is a mask token, the masked language model will give you a probability distribution as output over the set of vocabulary tokens. So suppose the prompt is I am masked to learn about HuggingFace, and the pipeline is fill mask. So fill mask is the task now, right? And you give the model BERT base case, and then if you pass the model the prompt, then what does the model output? The model outputs a score, that is a probability for each possible token. So there are top 5 tokens are printed. So this is the masked language modeling task, and you can also do it manually. Instead of using the pipeline, you can also do it manually using the sort max over the output layers. Okay. So this was a kind of a brief tutorial on HuggingFace. To learn more, you should really go and check out their documentation and read through documentation and get yourself familiar with the different classes and methods in HuggingFace. So thank you, and I hope you're enjoying the course. So happy learning.